Alright, so we're going to continue looking at properties of circles with our chords, with our angles, sorry. So we have central, vertex inside, vertex on, vertex outside. And so we start with a new definition with a secant line. So we've had tangent lines. These are secant lines that just go through a circle. This piece, just AB, that line segment is a chord. The whole line is going to be called a secant line. And so if we start to look at some of these properties, we can see that we have something in. I have two angles that I've created, or two arcs that I've created. And the way that this works, measure of angle 1 is 1/2 the sum of the arcs. So I add the two arcs up and then I take half of that. It's close to the same thing when it's outside. Angle 1 was outside. I have again two arcs that I have. And instead of adding these, I subtract my two arcs. So x and y get subtracted and I take 1/2 of that as we look to solve it. So if the angle is inside, you're going to add. If the angle is outside, you're going to subtract. And that's a key thing to keep in mind as we look through this. So if we look at the first one, the angle is outside, so I'm going to subtract, and these are my two arcs. So the way it looks like is I set it up. It's 1/2 of 130 minus 60, or half of 70, which is 35. So my first measure is 35. Now this one, we're going to ignore for right now. We didn't have enough information to do it. But if you look at the next one, I have angles in, so it's going to be where 85, that's the answer to this, is these two arcs, and I'm going to add them because it's inside. And so I solve for it, and I'm going to get 95 is my value for x. Alright? And then we can do something very similar with our line segments. So these are not angles, but the segments that are created by this have different properties, and it's not as simple as the 1/2 sum or difference. But the way it works is if they're inside, then I get this proportion where A times B equals C times D. This equation. And then for this one, if I look at the things that's outside, I get W times the whole thing, which is W plus X, and Z times the whole thing, which is Y plus Z. And then this one is T squared, there's no other piece, I can think about it as T plus 0, times Y times the whole thing as you go through it. Key thing to keep in mind is that these are segments. These are not angles. We're not looking at angles. We know we use these three formulas when we're dealing with segments. Right? Again, keep in mind that's the piece out, that's the piece out, and it shows up twice in our equation. So if we're doing that, we can solve some of these equations. I look at what I have in this case. That's a radius. That's also a radius. So that piece has to be the radius minus the piece that's out here, which is 50. So 125 minus 50 is 75. Right. And from there I can get x using the Pythagorean theorem. So 75 squared plus x squared is 125 squared. X is going to equal 100, right, if I plug through it. On the next one, this is a segment, and it's set up like our one of our segment ones that we just looked at. So it becomes x squared equals the thing that's outside, which is 3, times 3 plus 9, which is going to be 12. So x squared is 36, x equals 6. The next one again is segments, and I have the piece outside is 6, the piece outside is x, and so those are going to go outside. I get x times x plus 10 equals 6 times 6 plus 18, and I need to solve that. So I distribute and get x squared plus 10x, and then I get 36 times, or if I get, 6 plus 18 times 6 is 144. Now I have to hope that this factors. I bring everything over and set it equal to 0, and I try to factor it. Works out to factor as x plus 18 and x minus 8. The two solutions to that are negative 18 and 8. Only one of them makes sense. You can't have a negative value for x here. So we throw out one of them and we get x equals 8, and that's our final solution.